Welcome back to Soils 404-504, Water Quality in the Pacific Northwest. Today we're beginning a series of 3 lectures on groundwater quality. Today is Lecture 4, basically an introduction to groundwater quality. So when pollutants are released into aquifers, this is referred to as groundwater pollution. This type of pollution may be natural or it may be human-caused. The pollutant in question often creates a contaminant plume in the underground water-containing aquifer. Human-induced groundwater pollution can occur from many activities. This includes things like fertilizer use in agriculture, pesticide use in agriculture, or in urban areas. We could have leaking sewers. Additional sources of human-induced groundwater pollution can occur from effluent from wastewater treatment plants being discharged into rivers, and this discharge eventually leaches into the aquifer. Another source of groundwater pollution may be on-site sanitation systems, such as individual septic systems that contain a septic tank and a drain field. If the septic tank system is not maintained, the septic tank may fill up and chemicals would overflow that would eventually leach into the aquifer. Oil and gas drilling can result in groundwater pollution. The hydraulic process of fracking, which is a method that we use to get more oil and natural gas out of old deposits, may, if not used properly, may also result in groundwater pollution. Leaking underground gasoline storage tanks is another frequent source of groundwater pollution, particularly in urban areas. And waste from CAFOs, which we define as confined animal feeding operations, where we concentrate a large amount of animals in a small space. They generate a lot of waste. If this waste is not properly handled, some of it may eventually run off into surface waters, which can eventually become groundwater, or you may even have some leaching on site, and these wastes can enter the groundwater system. Now, there are natural groundwater pollution can occur also from many sources. Geologically occurring arsenic, geologically occurring fluoride, maybe geologically occurring mercury. There are natural sources out there that leak into groundwater systems. So in this introductory lecture about groundwater, I'd like to talk about some of the more specific pollutant types. Let's talk about our natural pollutant types. Let's talk for just a moment about arsenic and fluoride. If we take a look at all the metals and all the natural contaminants out there, probably the two that have caused the most problems for humans are arsenic and fluoride. They're the most serious inorganic contaminants to water supplies on a worldwide basis. The World Health Organization of the United Nations estimates this. Arsenic and fluoride contamination of groundwater is a serious problem in countries like China, Bangladesh, and India, a very large problem in many Asian countries. Another type of groundwater pollutant are pathogens. Pathogens are a serious problem in shallow wells or in shallow aquifers. Pathogens in shallow aquifers have been known to cause cholera and diarrhea. We usually think of cholera and salmonella and other pathogenic organisms in drinking water as coming from surface water. But if the wells are very shallow, these pathogens can leak into the groundwater and contaminate that drinking water. Also, we see in many areas of the world, shallow groundwater, where we have hand-dug wells, is often contaminated with human feces and causes many diseases in humans. We will talk about pathogens in groundwater in a little bit more detail when we get to the drinking water portion of the class. Another pollutant type is nitrate. Nitrate's so important, we're going to spend the next couple lectures talking about nitrate as a pollutant and nitrate as an indicator of groundwater contamination. So we're not going to dwell on it right now. Another type of pollutants that get into groundwater systems are organic compounds. Organic compounds are compounds that are made by humans. They contain carbon. Organic compounds are used for a variety of chemicals. We use them for agricultural chemicals. We use them in many manufacturing processes. There's literally hundreds and hundreds of different organic compounds that have been identified in shallow groundwater wells. And of major concern are pesticides. Hundreds of different organic compounds have been found in groundwater, and several of them are considered toxic. Another type of pollutant are the metals. Metals can find their way into groundwater through manufacturing processes. Metals are produced by mining, metal refining. Sometimes we have metals in solid waste disposal. Sometimes we have pesticides that include metals. The metals are part of the pesticide, particularly our first generation pesticides that are historic pesticides. We don't currently use them, but we have in the past, and they're still around. The most toxic metals that we're worried about when we talk about groundwater pollution include lead, cadmium, and chromium. And we'll say a little bit more about metals later. Another pollutant type that we're worried about in groundwater are pharmaceuticals. Pharmaceuticals are a group of chemicals that is an emerging groundwater issue. It has already turned into a surface water issue, but it's an emerging groundwater issue. The major pathway of contamination of groundwater is treated effluent from wastewater treatment facilities. Pharmaceuticals pass through these wastewater treatment facilities, and they get released in the discharge water. If any of that discharge water leaches into the groundwater, we can contaminate. We don't have good information on the potential toxicity or harmfulness of pharmaceuticals. There are individual studies that have shown that pharmaceuticals may cause problems in fish. They may cause problems in other aquatic organisms, but at the levels they're found right now, there's no definitive information that these are toxic directly to humans. But it's a category that we're going to hear more and more about. You'll see more and more research done on pharmaceuticals in water supplies, particularly drinking water supplies, but this is a concern for groundwater, which is usually a drinking water supply. There are other contaminants that we're not going to spend any time on right now. Petroleum. If we have spills, we can get some leaching into groundwater. We have chemicals like radon, radium, uranium. They're radionuclides that can leak into groundwater systems, both naturally and both because of things humans do. Saltwater intrusion along the coasts. If we pump too much groundwater from the ground and we're near the coast, some of that water in the aquifer may be replaced by salt water. And of course, that's not pure enough for most human uses, so we consider that a form of groundwater pollution. In summary, groundwater pollution is a worldwide issue. We've talked about it in the United States for 50 years. Europeans have been very interested and concerned about groundwater pollution in the last 30, 35 years. Virtually every continent except Antarctica has groundwater pollution issues. The issues are well identified in the United States and in Europe. But even on continents where we don't know very much about groundwater, we're starting to see it emerge as a problem, groundwater pollution. Let's just spend a few moments talking about some of the causes of groundwater pollution, very much related to pollutant types, but I just thought it was worth some time to go over these things. Some of these causes are naturally occurring, geologic causes. To improve drinking water for many in the third world, wells for drinking water have been drilled. In some cases, this has backfired. As pollutants like arsenic, when we drilled wells, the arsenic became available and got into the drinking water and has caused big problems. And it's kind of ironic that in places like Bangladesh, arsenic is now as big of a problem in drinking water as were pathogens, human pathogens. And in many cases, to provide decent drinking water to people, we went away from using surface water and went to groundwater, and we changed problems. We changed the pathogen problem to an arsenic problem. Another cause is on-site sanitation systems. Humans are capable of designing on-site sanitation systems that protect the environment. However, a lot of these systems out there are not properly designed, or they may not be maintained correctly. If they're not maintained or designed correctly, the liquids in these on-site sanitation systems have pathogens in them and chemicals. If they're not maintained right, they can leach into groundwater. And we have to realize that we can't put on-site sanitation systems in every place. Not all soils are suitable for these type of sanitation systems. And in the United States, we're talking about septic systems, septic tanks, and drain fields. We may be talking about leaching pits and things like that. But if these on-site sanitation systems are not designed correctly, or not maintained correctly, or put on a site that's not suitable for them, they can cause problems. Sewage. It really doesn't matter whether it's untreated or treated in this discussion. Sewage is discharged into surface water bodies. But there's a connection between surface and groundwater. So surface water can become groundwater with time, and the pollutants in the treated sewage may cause problems. Groundwater has been linked. We've seen shallow groundwater wells linked to diseases like skin lesions on people, bloody diarrhea, and dermatitis. And we know that these are cases of groundwater causing these diseases in humans. Again, these are in shallow wells where these diseases have been present in surface water and leached into shallow wells. We're talking about wells that may only be 4, 7, 8 feet deep. In a lot of parts of the world, our wells are hand dug, and there's not much protection. Another cause would be fertilizers and pesticides. Throughout the world, fertilizers and pesticides are widely found in groundwater. This is because fertilizers, particularly nitrogen fertilizers, leach. They readily leach. You add water to the soils and the fertilizers move with the water. So we see nitrates widely found in groundwater because they're leachable. If we apply too much nitrogen fertilizer to soils and we get a wet event, too much rain, or we irrigate and we apply too much water, we can get the nitrates into the groundwater. When we talk about water pollution and surface water pollution, we're talking about nitrogen and phosphorus. We don't really have much phosphorus in groundwater because phosphorus is not a chemical that readily leaches through soils. Generally, phosphorus stays where you put it in the soil, and if we have phosphorus problems in water, it's surface waters, and that's because we've had erosion from soils and the phosphorus is washed off the surface into a surface water body. But when we talk about fertilizers in groundwater, we're usually talking about the nitrate form of nitrogen. And again, we're going to detail nitrates more specifically in lectures 5 and 6 in this course. Commercial industrial leaks are a major problem. We have both inorganic and organic chemicals that are found in groundwater that have been linked to industrial leaks and industrial accidents. Also, contaminants in acid mine drainage are especially prone to leaching because the conditions are very acid. A lot of these chemicals leach readily and can contaminate groundwater. In addition, leaking underground storage tanks are a major source of groundwater pollution in most urban areas of the United States, and we're usually talking about underground gasoline storage tanks. After a while, these underground storage tanks basically deteriorate, and some of that gas can leak out and enter the groundwater. Today, we have regulations that require these underground tanks be double-walled and regularly inspected, but we've got hundreds of thousands of old tanks in the ground in the United States and throughout the world that are potential problems to groundwater. And indeed, in many cases, we have many states that say underground gasoline storage tanks that leak are their biggest cause of groundwater pollution. There are also many industrial solvents that in the right environment will leach and contaminate groundwater. Common chemicals like PCE and vinyl chloride are examples of these chemicals that have leaked into groundwater and become contaminants. Something that is relatively new is a process called hydraulic fracking. And sorry, I have this misspelled. Fracking, F-R-A-C-K-I-N-G, or fracturing, hydraulic fracturing. This is a relatively new technique that's used to recover oil and gas resources. When properly used, groundwater contamination from fracking is minimal. However, when improperly practiced, due to technical problems, where the system's not designed properly or not installed properly, the groundwater can be contaminated, particularly the casing of the well, where the fracking chemicals are put down into the sediment. There have been several recently published papers that have identified this technique as a groundwater problem when not correctly used. So this is a pretty controversial area right now. Another major problem for groundwater contamination is the leachate from landfills, from old landfills that have been closed, landfills that are below state-of-the-art. Leachate from landfills, if we've got chemicals that dissolve waste, or from the waste as they dissolve. Remember, in our landfills, we have things like paints and waste materials and stuff like that. If water moves through the landfills, they create a toxic leachate, and this leachate can eventually enter the groundwater and cause serious problems. We have several incidents around the world and in the United States of old closed landfills that have leaked and become major problems. Probably the most famous old closed landfill in the United States that has caused a lot of problems is called the Love Canal. The Love Canal was an area in Upper New York State. The Love Canal was basically a toxic waste dump. And the dump was closed and a housing development was put on it. And in a short period of time, many of the residents that lived in that subdivision got cancer. They had a very large increase in cancer in the neighborhoods that was contaminated. Eventually, the Love Canal was closed down, and eventually this led to a lot of legislation to really see how landfills, particularly hazardous waste landfills, were closed, how they were remediated, and the separation that should be between a closed landfill and a housing development. There are plenty of other causes too. Chemical spills during their manufacture, chemical spills during their transport. You've got a large semi-tractor trailer carrying a hazardous chemical down the road, and there's an accident, and this accident occurs near a water body. You got to worry about leaching. Illegal waste dumping. Sometimes it's a lot cheaper to get rid of hazardous material by illegally dumping it, and that can contaminate groundwater under the wrong conditions. Mining operations, the use of road salt. If that leaches, that can contaminate groundwater. De-icing chemicals, particularly in airports, where in the winter, many of the planes have to be de-iced before they take off, so you have a lot of chemical present. Urban runoff is a major problem. That runoff eventually reaches a stream, and the chemicals in that runoff can leach into groundwater. And even atmospheric contaminants. Any contaminants that fall out of the atmosphere, such as air pollutants, once they reach the earth, they become part of the hydrologic cycle. And through the hydrologic cycle, some of those chemicals can leach and eventually end up in the groundwater. So there's lots and lots of causes out there that cause potential problems. So let's take a look at prevention of contamination. I think the best way to take a look at this is to take a look at what's called the precautionary principle. I think it's a very good principle. Basically, it states that where there are threats of irreversible damage, lack of full scientific certainty shall not be used as a reason for postponing cost-effective measures to protect environmental degradation. So where there are threats of irreversible damage, the lack of full scientific certainty shall not be used as a reason for postponing cost-effective measures to protect environmental degradation. This is part of the European Union's water policy. So we need prevention of contamination, even if we're not 100% sure the technology works. We cannot use it as an excuse. If we're not 100% sure, we can't use that less than 100% assurance as an excuse not to do something. So some of the things we do to prevent contamination. There's lots of information in the scientific literature about this. Wanted to just bring up some points. One of the major things we do is we monitor groundwater quality. Lots of states, lots of countries, lots of counties, lots of cities have groundwater quality monitoring programs. These are simply common methods that is used to protect water quality. Many monitoring programs have been implemented around the world. Monetary investments should be large enough for long-term monitoring. It's not something you want to do for a year and then forget about it. It's something you want to do over time so you can track whether contamination is getting less or greater. There is a positive relationship between long-term monitoring and drinking water safety. Where groundwater monitoring programs have existed and been long-term, there is a tendency that the drinking water from that groundwater is safer for the public. So that's one thing that is done. A second method that can be used for the protection of groundwater and prevention of contamination is land zoning. We zone to protect groundwater. Land use zoning maps have been used with success by water authorities throughout the world. People have created things like aquifer vulnerability maps, source protection maps. This is a tool that is, science has gotten more sophisticated, planners have gotten more sophisticated. We've been able to use land zoning to protect our groundwater resource. If we take a look at aquifer vulnerability maps, vulnerability map development enhances groundwater quality protection. Basically, a vulnerability map are several layers of information that are overlaid to produce a valuable map. There are several different types of vulnerability maps out there. I thought I'd just toss out a couple. One that's pretty famous is the index-based mapping method that's called GOD. And GOD is an acronym that looks at three factors in the basically three overlays in a aquifer vulnerability map. Let's take a look at GOD. The three factors: the degree of groundwater hydrologic confinement. That's what the G is for, groundwater hydrologic confinement. The O stands for the geologic nature of the overlying strata. And the D stands for the depth to the groundwater. Actually, the D should be capitalized. And this is a very simple aquifer vulnerability map, but when these three layers are laid together or overlaid, you can get a good picture of where the groundwater is most vulnerable. Another common method that is used to produce a groundwater vulnerability map is EPA has a method called drastic. And drastic just simply stands for several things. First, we look at the D stands for the depth of the water table. The R stands for the net recharge of the aquifer. The A stands for the aquifer media. The S stands for the soil media. The T stands for topography. The I stands for the impact on the vadose zone. And the C stands for the hydraulic conductivity of the water in the aquifer. So there's several methods out there. You can go to the scientific literature and learn a lot about groundwater vulnerability mapping. Again, looking at these aquifer vulnerability maps, there are a lot of debates raging in the scientific community about these maps. There are some people that say we need to create a vulnerability map for a particular county or a particular area, and one map works well. And there are others saying we need to make the vulnerability map pollutant specific. If nitrates are prevalent in our area and leaking underground storage tanks, we should have a vulnerability map for nitrates and a vulnerability map for underground leaking storage tanks. And because of the nature of the chemicals, the gasoline and the nitrate being a little bit different, the vulnerability maps should look a little bit different. Another way we can prevent contamination is through a process called source protection mapping. And this is where we capture areas around an individual groundwater source, map those areas. Potential pollutant sources can be located a distance away from our protected groundwater source, and this protects our groundwater. To use source water protection mapping, you use equations to define groundwater flow, and you use simulation models. An example would be the WHPA to delineate capture zones in a wellhead protection area. The simplest forms of zoning employs fixed distance method, where specific activities can be excluded. So you have an aquifer that's a source protection area that you want to protect that aquifer. You delineate distances that certain activities have to be away from that aquifer to protect it. You can exclude specific activities around it. Another way we can prevent contamination, we can locate on-site sanitation systems. Where we locate them, how we locate them. Let's be as scientifically valid as possible. On-site sanitation systems can be designed to prevent groundwater pollution. In almost every case, you can design a system that will work. There are distance guidelines out there that have been developed to estimate safe distances between an activity and a vulnerable groundwater source. We use those distance guidelines when we locate our on-site sanitation systems. So locating on-site sanitation systems, we have operating criteria. Some of them are simply distances away. There should be a horizontal distance between drinking water source and a sanitation system. Depending on the stratum, the depth of the groundwater, and other factors, there's a fixed distance. There should be a vertical distance between the drinking water well and the sanitation system also. Other operating criteria that you need to consider is the type of aquifer you have. What direction is the groundwater flowing? Do you have impermeable layers? What is the slope and surface drainage? All these need to factor in. What is the volume of leaking wastewater from a sanitation system? And how does your system fit in the larger area that the aquifer covers? There are lots of programs out there that help a homeowner do this. So if you have your own well, if you live in the rural areas of the country, you have your own well, there are systems where you can actually get these systems. They're public information, and you can actually do a source water protection for yourself and make sure your clean water, your drinking water well, and your sanitation system is separated far enough. Probably the most popular program is called Home Assist. There is a Home Assist program for Idaho, for Oregon, and for Washington. It's a series of brochures that you download, and you can go through and you can do a routine check if you live in a rural area of how safe your water supply actually is. You can't talk about prevention of contamination with at least saying something about legislation. We have to consider institutional and legal issues. Water is a very complicated system in the western United States. We need to legislate water issues based on the success of our groundwater protection policies. Where groundwater protection policies have been successful and protected the quality of groundwater, we need to work this into the legislation so we have the best information available. And then finally, as our introduction to groundwater, we need to say a few things about management. You have a contaminated aquifer. What do you do about it? You have to take a look at options for remediating contaminated drinking water. You need to contain pollutants. If you've got an aquifer that has some nitrate in it or it has a plume of gasoline in it, you need to contain the pollutant in that spot in the aquifer to prevent that pollutant from migrating further and adversely impacting more people. So that's an option. Another option is simply removing the pollutant from the aquifer. May not be very easy. And then if the aquifer is large, how about remediating the aquifer by either immobilizing or detoxifying the contaminant in the aquifer while it's still there? Basically, remediating the aquifer in place. Or your other option is to take the water out. As you take the water out, treat the water before you actually use it. Recognize that you have a contaminated aquifer, you pump the water out, and that water goes through a treatment phase before it's used for any other human use. Another option is, if the contaminant in the aquifer will cause too many problems, just abandon the use of the aquifer's groundwater and find an alternative source of water. That's been done several times in the United States. It's a problem worldwide because lots of times there aren't a lot of aquifers or different sources of water for people to use. They basically have to use what they have. So when we talk about removing water from a contaminated aquifer and then treat it before humans actually use it, we call that point of use treatment, POU. There are water purification system devices that can remove some types of contaminants prior to drinking. So you would treat the water at the point of use. And we will talk about these types of point of use water treatment devices when we talk about drinking water. So groundwater remediation, it's a lot more difficult from a long-term basis to deal with groundwater than surface water. So if you have surface water pollution, you can remediate that by changing your practices. However, if you have groundwater pollution, the pollution is there, and that aquifer will remain contaminated for a long period of time. So if you have pollution in your groundwater or your aquifer, there are some physical, biological, and chemical treatments that can remediate the water, but it's usually going to be very expensive. Because of that, lots of times these aquifers are abandoned as a water source. If treatment or remediation of contaminated water is deemed to be too difficult or too expensive, abandon the water, abandon the aquifer, and then find an alternative water source. And again, that's not always easy to do because in lots of areas, particularly in the western United States, water is scarce. Water is precious. So the information I presented in this lecture is just to give you an overview of groundwater quality. A lot of the principles involved with groundwater quality will be talked about in lectures as we go through the course. Thank you for your attention. Where we don't have good models, where we don't have good monitoring, you're starting to see groundwater pollution emerging as an issue. And if we take a look at different pollutants in Africa as far as officials ranking them as far as level of concern, we see that nitrate pollution is considered probably the biggest problem in groundwater pollution in Africa, followed by pathogens. Again, this would be related to shallow wells, hand-dug wells. Organic pollutants such as pesticides and manufactured chemicals. Salinization along the coast, where people have removed too much drinking water from the groundwater supply, and some of that water has been replaced by salt water. and then acid mine drainage. Of course, Africa is a continent that is thought to be very rich in resources that people want, so there are lots and lots of mines with very little protection to protect that acid mine drainage from leaching into the groundwater. Well, in addition to pollution